Hi everyone. So first of all, thanks to the organizers for giving me this opportunity to talk about the work that's going on with Gina Neubron and Zoran. I think none of them has joined it. So yeah, but the topic is like impact of small X evolution on the nuclear deformation and the application of it to the isobar condition. So this is like a brief outline. I'll be talking about the introduction, which includes some idea about the effective field theory, and then I'll talk about the methodology, which includes quantum evolution and how do you put Jim-Walk evolution on the lattice. Then I'll talk about the results, which includes the effect of the Jim-Walk evolution on bunch of nuclei, for example, uranium, neon, and then these isobars. And I'll conclude with summary and what can be done in the future. So let me start by setting up the stage by talking about the different stages of the heavy ion condition. So you know that when two levels contracted nuclei pass through each other, they leave behind a debris of highly excited state of matter, and it continues to expand longitudinally. Now, the system is initially far from local thermal equilibrium, but by the time it reaches 1 from U over C, the plasma of the quark and gluon is close to the thermal equilibrium, and one can use the hydrodynamics to explain the subsequent evolution. Now, over here, the fireball expands and cools down, and it happens until the temperature falls below some critical value, where the fluid falls apart into a gas of hadrons, which then scatters quite a few times among themselves, and then freely streams towards the detector. Now, even in the pre-equilibrium stage, we are normally interested in the description of this dense colliding nuclei which collides and the energy deposition. So now let me start by talking about the light cone kinematics, which turns out to be the most efficient way of dealing with the high energy static processes. So let's consider Z to be your longitudinal axis of collision, and imagine an arbitrary 4-vector view mu. Then the light cone coordinates V plus and V minus are given as algebraic sum, and the difference of your V0, which is the D, and V3, which is the longitudinal coordinates in your Minkowski space. And V1 and V2 are taken as your transverse coordinates. Now, one can take two 4 vectors, P mu and X mu, and can calculate the invariant scalar product, which turns out to be this, where your P minus and P minus and X plus, V minus and the X plus combined in this way. Now, based on this invariant scalar product, we can say that P minus can be interpreted as the light cone energy, because X plus is your light cone time. Light cone time, and P plus can be interpreted as your light cone momentum, because X minus is your longitudinal coordinate in the light cone coordinates. Now, people define rapidity, which is given as the K plus and K minus component of your light cone momentum. And by using the dispersion relation for the light cone coordinates, which includes the K plus and the K minus component, K plus and the K minus component can be expressed in terms of your invariant transverse mass. And using this dispersion relation, one can write rapidity in terms of your K plus component of your light cone momentum and your invariant transverse mass. Apart from rapidity, people also define this longitudinal momentum fraction, which basically tells you how much momentum of a particular hadron does a parton carries, and it is given as if K plus is the momentum of if P plus is the momentum of the hadron, and then X is defined as the K plus, which is the momentum of the partons times divided by the momentum of the hadron. Now, let me start by talking about the McLaren-Bellingopanen model, which back then was which till now is a very famous model, and it helps you in describing the heavy nucleus. So let's consider that your nucleus is an infinite momentum frame, which means that your light cone momentum P plus is very large, and you also assume that you have an infinite transverse extent, and the nuclear distribution is homogeneous. Now, you can have two types of partons which carries large longitudinal momentum fraction, and they are essentially your balanced partons. So since you're working in the infinite momentum frame, you will have Lorentz contraction, and because of this, the nucleons will appear essentially two-dimensional. Now, there are other kind of partons, which are the V partons, and they carry small longitudinal momentum fraction, and they will be highly delocalized in the longitudinal direction. So over here is a short description. All the dots are the localized components, are the valence partons, and then these small X gluons are highly delocalized in the along the longitudinal direction. Now, since V partons are highly delocalized, they see the valence partons as infinite thin sources of the color charges. Now, another silent feature of this V parton is that they have a very short lifetime. So by using this uncertainty relationship, one can calculate the lifetime of the parton, and it turns out to be directly proportional to your longitudinal momentum fraction. So for the V partons, the lifetime would be small because X is small, but for the large X partons, that is the valence parton, the lifetime would be large. So based on that, one can say the V partons will see valence partons as a static color sources. Now, large X partons carries large momentum. And because of that, they will be unaffected if they emit a gluon or absorb the gluon. And hence, they will be treated as a recoilless sources of the color charges. Now, the large X partons can be expressed, for the large X partons, you can write down the color current. And in the ultra-relativistic limit, which is the infinite momentum frame, the X minus direction will be infinitesimally thin. So the color currents are given as are proportional to your delta X minus component. And then they are given in terms of your color charge density, which is your rho A, and A is your color index. And since we are working in the light cone coordinates, it's only the plus component which is enhanced by the Lorentz factor, and the other components are essentially zero. So the color current, the J plus, is given as the has a transverse dependence on this color charge density.
I have one question.
Yeah.
I have no time to go over numbers, but you say we partners have very short lifetimes, but at the same time they're delocalized.
Delocalized, yes.
If something short lifetime cannot move far, so what?
No, but
I mean, they move at most they can move at sea, right?
yes.
So how come they can be very short lifetime and move far?
No, but if they have a short lifetime, you are just thinking from their reference point of view, they have moved a large distance, and at the same time, we are seeing many large X partons. So it's from there, from that.
The number, what is short
lifetime,
and how far they move?
For example, if you put X to be like, let's say 0.10 power minus 3, and put P plus value or something like this thing. At the moment, we are considering infinite momentum frame. So infinite momentum frame will have like a large P plus, and still you will have like a large lifetime. But if you put down the real numbers, it will turn out to be, like, I've never calculated it, but you can take X to be 10 power minus 3 or minus 4, P plus to be in some GeVs. TeV or G, yeah, TeV, because some TeV, and I don't know, some GeV, and it will turn out to be a large number.
So this is the lifetime calculated in the light cone.
Yeah.
And then you have to boost back to the mid rapidity. You have to go back, talk about the lifetime. If you talk about from the lab frame, people look at the lifetime of the V parton. Are they long-lived or they short-lived? Right?
They will be short-lived. The V partons are always short-lived compared to the valence partons. So this, when I say short lifetime, it is based on the it is with respect to the lifetime of the valence partons. So valence partons are long-lived in the frame of reference of the V partons.
But now you go to mid rapidity, then the lifetime will be even shorter, right? Because now you're not in the rest frame, but you're actually in the lab frame.
Yeah, but again, it will be shorter. And
yeah. So the relative fraction won't change.
Yeah, relative fraction of the V and the valence will change. This is the point. Yes.
But in terms of, I think Paul asked, like, can you give a number like let's say X equal to 10 to the minus 3? What is the lifetime?
If you put P equals 5 TeV, you get M equals 1 GeV, and you get 10 fermis.
So the M is like a saturation scale, or?
No, M is your transverse invariant mass, which is it will be like energy plus your K plus energy, yeah, K pop squared plus energy squared, energy, yes. So it will be some order of GeV, but not essentially your QS.
So those are the mass of the part of the V partner.
Yeah.
It's like a virtuality.
Virtuality. And that will do.
I think we can. I think this no, this is.
There will be some orders of Fermi for the valence pattern, it will be a little bit more than that. It will be less because you're having everything at a very micro
That's
scale.
all
I don't know
it
when
is. I try to get the sense. I mean, what I get an idea, a qualitative idea what this physical picture is, but I have no idea what it actually is.
I unfortunately have never calculated the numbers. And it's like, for example, you have a nucleus and you're boosting it at a very large energy.
I understand that. I
Yeah,
understand it. I understand all the X pluses and X minuses and so on, but what it is in practice.
In practice, I've never, I'm sorry.
So in the
That's all right.
in the rest frame, how do we view the lifetime? What does the lifetime mean in the rest frame?
Or
So
let's
it's
say if you
basically, when
pass-
I say the lifetime, I just want to emphasize on the fact that one of them will be a static object and the other will be a
Sure,
dynamical
sure.
object.
That's
So this
all
is
what he's doing.
Okay.
So all based on just.
Okay, now, yeah, let's have an idea of like how do you think about the color charge densities and how they are generated. So imagine you have an external probe which is probing the nucleus, and this probe will resolve like a certain transverse space, let's call it delta x, and in the transverse direction, it's probing this delta x size like delta x, but in the longitudinal direction, this probe can couple to partons from different nucleons, and these different nucleons are uncorrelated. So based on these different nucleons are uncorrelated, but one can essentially calculate the number of these sources, which are the number of these valence partons, and it is given as the product of the density of this valence quarks, because these are the sources, times the transverse area. So you can write down the number density S, and delta S is the size probed by the external probe in the nucleus. And it turns out to be, this number turns out to be proportional to the atomic mass to the power 1/3. So for a large nucleus, the number of these sources are very large. And if you do some, you can write down, replace these number A with your, if you can replace your R with your R naught A raised to the power 1/3, and R naught can be written in terms of your confinement scale. So when you use this, you get the N in terms of this formula. Now, since you're working in a small x, since you're talking about the small x, or you're talking about the very large nucleus, these valence quarks, the number density of the valence quarks will be very large, and because they are originated from the uncorrelated nucleons, then based on the central limit theorem, you can say that the color charge density will have a simple Gaussian probability distribution. And over here, I have written down the 1 and the 2 point function of this color charge density. The 1 point function will be 0 because on average these objects are color neutral, and the 2 point function is given in terms of g squared mu, and this mu squared can be related to this. The average color charge squared of the valence quarks per unit transverse area, and AB are your color index. Now, let's try to go towards an effective theory. So imagine you have a nucleus at a very low energy, and you boost this nucleus. So when you boost it, more and more gluons will emerge. So the gluon density will grow. Again, I'm just kind of revising the things that we just talked about. So again, you define a parton momentum fraction, and based on this parton momentum fraction, you will have two types of partons: the valence quarks, which will carry the large momentum fraction, and the small x partons, which we call the V partons. And using the Heisenberg uncertainty principle, you can calculate the temporal and the longitudinal extent. Based on this, we'll have this picture where one of them will be highly delocalized and the other will be localized with respect to each other. Now, one can say that if you keep on boosting the gluon, will it mean that the gluon density will grow on forever? And the answer is no, because at some point, non-linear effect will start to show up, that is, gluons can recombine with each other, and this will tame the growth. And this term, this entire phenomenon is called the gluon saturation. So gluon saturation basically measures the effect of this non-linear interactions. And this is characterized by this scale, QS, which is given, which has a certain dependency of your on your atomic mass and your small x, which is your the longitudinal momentum fraction. So higher the mass of the nucleus, higher the saturation scale.
So this the time and the length is always referred in along the z direction.
Mhm.
So when you see they are short-lived is in the z
z
direction, short-lived.
Because that's the direction I'm considering my boost.
But then their transverse size can be larger.
Yeah.
Right?
But transverse scale, like on transverse size, you have the saturation scale, this QS, which will control the size of the gluon in the transverse direction. Okay, now with this we can talk about the effective field theory for the high electricity, and it's called the color glass condensate, and it is basically a theory for the sources and the fields. So if you again consider the nucleus, which is boosted along the k plus direction, then you can consider a scale which is x naught p plus, and this is the cutoff scale which distinguishes between the small x and the large x partons. So the small x, you just saw that the large x partons can be expressed in terms of the sources, and these sources are given in terms of the weight functional. They are expressed in terms of the weight functional, and the small x partons are expressed in terms of the gauge fields. So these fields and the sources are related by your Young-Mills equation. Now, the fast, as we just saw, the fast color sources are represented by the color currents, and they are expressed in terms of your color charge density. And just because of the uncertainty principle, we saw that they can be taken to be random and static. Now, these color currents give rise to the gauge fields, and the gauge, these two degrees of the freedom are related by your Young-Mills equation, where d mu is your covariant derivative, and a mu is your gauge field, Ta is your generators in the fundamental representation, which is related to your antisymmetric tensor. Now, once you have this thing, you can always calculate observables. And when I say observables, first of all, you draw sources for a given weight functional, and these sources give rise to the gauge fields. Now, you keep on doing this thing, like you keep on drawing sources from a particular weight functional, and then you average over all such events in order to compute the expectation value of the observable. Now, so far, what we saw that the quarks and the gluons were the degrees of the freedom, but the more convenient degree of the freedom would be your Wilson line. So let me illustrate it. So imagine that you have you have your quark and you want to interact. I'm sorry, I'm like, oh God. So imagine you have a quark which is moving along the k minus x minus direction, and it has a large k minus momentum, and because of the dispersion relation, the k plus momentum would be small, and this quark has to interact with the target which is your shock wave, and this shock wave will contain the classical fields of the nucleus. Now we will always work in the Eichhorn approximation. That basically means when a quark passes through the shock wave, it's only the color which gets rotated. So we had the color J, and after passing through the shock wave, it became I. But rest of the things, for example, its transverse position, its transverse momentum, everything else will remain as it is. And this is given, this color rotation of the quark is expressed in terms of the Wilson line. So when I say a quark has passed down the shock wave, that basically means it can interact multiple times with the gluons of the nucleus, and since it can interact as many times as possible, you normally have to sum over all such interaction, and this is given by taking the summation on Ga plus, where A plus is the classical background fields of the nucleus. Now, this entire color rotation is encoded in the light like Wilson line, which for the quark is given as a summation over the direction, over the longitudinal direction that it has passed through the nucleus, and A plus is a gauge fields of the background nucleus, and it has a dependence on your Z minus, the direction in which it is passing, and the transverse spacing. And you always have to take into account the path ordering. Now, similarly, for a gluon interacting with the target, you can write on the Wilson line. And again, this is given in terms of the A plus and the TC, and the generator over here will be in the adjoint representation. So based on this thing, we can say that the interaction of the gluons and the quarks are expressed in terms of the Wilson line. So we can call the Wilson lines as the building blocks of the color glass condensate.
Can you go back to just this K plus? Those are the gluons. So.
No, this is the momentum of the quark. At the
quark.
moment,
Okay, but there's the K minus is large. That's in the
so I'm
in the
considering.
frame.
Yeah, I'm considering that my quark is moving along the X minus direction, and it has such a large K minus component.
Yeah.
And just because of the dispersion relation that we saw for the light momentum, the K plus component would be small.
That's the like
Assumption.
some momentum involved in colliding with a gluon, right?
Momentum involved?
It's not like sort of like because your K perp is sort of like scattering strength with the gluon field, right? The K perp. What is the K perp? KT.
This K minus K plus everything is associated with the momentum of the quark.
And then the KT.
KT is the transverse momentum of the quark.
Which are generated by the scattering itself, or
No,
or intrinsic.
It's intrinsic. Like you have a quark which is coming with this momentum and it is interacting with the gluon fields of the target.
Okay.
The entire information about the gluon is in this part. It's in the A plus form. A plus. This is the where the gluon.
What controls the KT?
KT is an external. It's an intrinsic property of the quark. I'm just assuming that my quark is coming with some momentum.
Transverse momentum.
Transverse momentum, like momentum, and it is interacting with the shock wave. And the shock wave contains the information about the background field of the nucleus. And when I say background field of the nucleus, that basically means the gluonic fields.
But the K plus is sort of like you're going to the backward, right? You're going to the gluon rest frame, right? Right. That's the K perp is in the gluon, almost gluon rest frame.
Yes.
And that's what is relevant for the scattering with the gluon, right?
Yes, but when I say iconal approximation, that basically means the gluon did not affect the K perp of the quark. This is the iconal approximation, that the transverse momentum, the transverse position, everything of the quark will remain as it is. So it is not being changed.
Yeah, so naive expectation would be that polar field is zero.
The
Naive expectation would be, I mean, the nucleus has no color, right? But so what is it? Is it a fluctuating field or?
It has color because the color has been rotated. Like you started with some color J, and after interacting with the target, the color got rotated. That basically means it has some interaction happened, and this influenced the color of the quark.
Not
But I think it's asking, so those A plus, those are classical gluon fields, right?
Yeah.
And there's fluctuations that is causing these rotations.
That's what I would say, but you have to need some model for that.
Sure, yeah, I think so.
So we didn't get this.
No, it's just, you have a model for the fluctuations that you're going to use.
Yes.
Right.
Yeah, that's the MV model.
Yeah, you should just introduce it, right? This is the one that you just introduced. The one.
Yeah, the MV model. Yes, the McLaren-Manning model, which describes how do you define this color fields. And now I'm just trying to describe, like, if you have a model, everything is there, but what will be your convenient degree of the freedom for doing such kind of scattering processes?
Right,
And I
but
think
what I'm saying is that naive model would be A plus is zero, A plus C is zero.
Yes, but as you said, it's a fluctuating field. You have the 1 point function, which is 0, and the 2 point function, which is a Gaussian. Okay, so I think this is exactly it. Maybe which is
Where?
It's 5
this
yeah,
is the MV model that I was talking about.
That would
Yeah, this is the.
Okay. Okay, okay.
Okay, so based on this, I can say that my Wilson line are the building blocks of the CGC, and to shed some light on this idea that all the scattering processes in the QCD can be written in terms of the Wilson line. Let's take an example of a totally realized cross section where your virtual photon will scatter off the color field of the nucleus. So the cross section is given as a combination of two terms. The first term, which will contain the information of the virtual photon splitting into quark anti-quark pair, and then the second term, which contains the information of the quark anti-quark scattering with the color field of the nucleus. Now, this part comes from the optical theorem, and you see that you can construct a simplest dipole correlator given in terms of the product of the Wilson lines, where V contains the information of the quark interacting with the target, and V contains the information of an anti-quark interacting with the target at point X quark and Y quark. Now, the other part where you have the virtual photons splitting into the quark anti-quark pair, it depends upon your transverse dipole separation, your virtuality, and the longitudinal momentum fraction of your quark. Now, instead of using your X perp and Y perp, you can always do a change in this variable, and you can write it in terms of a dipole separation and the path parameter. So this example basically tells you that the DIS cross section can be expressed in terms of your product of the Wilson lines. Now, so far what we were doing is we were having a weight functional, and this weight functional comes from a model, like the model I chose, MV model. And what we were doing, we were constructing the observable at the same point where the weight functional was defined. Now, what happens if I probe the observable at point X, which is smaller than this X naught? Now, so far our classical theory was working perfectly fine, but when you go, when you probe the observable at X less than X naught, the quantum corrections will turn into account. So what happens is, like, when you're boosting, you are opening up the phase space, and now your quarks and anti-quarks can emit more and more gluons. So let's consider that your quarks, this is again from the same figure where you have a quark and anti-quark passing through the scattering of the color field of the target. Now what I'm assuming is that either the quark or the anti-quark can emit a gluon or absorb a gluon. So this gives rise to two types of correction, two types of diagrams: the real diagrams in which the emitted gluon passes off the shock wave, and the other one in which it is absorbed before the shock wave or after the shock wave. Now, these type of so when you have such kind of splitting of the entire quark gluon and the anti-quark pair, the quark and the anti-quark can scatter off the color field of the nucleus, and this gives rise to two types of diagrams, which are the real diagrams and the virtual diagrams. The virtual diagrams are needed in order to get rid of the divergences that occur because of the real diagrams. Now we can take this large NC limit. When I say large NC limit, basically that means you are considering so many colors, and your gluons can be considered as a dipole. Basically, instead of having one dipole, now you can have two dipoles. The one which is your quark anti-quark, and the other dipole in which I call my gluon as another quark anti-quark pair. Now these two dipoles will can interact with the target, and you can write down. So our main question is, like, how does the dipole scattering amplitude look at a larger rapidity? And this can be expressed as the product of the scattering of the two daughter dipoles. And when you want to construct, like, what happens, you basically write down it in terms of the product of two dipoles, where R prime is the dipole coming from your gluon, and this R minus R prime is the dipole separation from your parent dipole, and the other one. So basically, you take this term and you subtract the original dipole, and this will give you the information of how does the dipole scattering, how does the dipole scattering look at a larger rapidity. Now it contains two types of terms. The first one is the linear term, and it contains the virtual information and contains the information from the virtual diagram. And the other one is the quadratic term, which contains the information about the real contribution. Now, if you consider the weak scattering limit, when I say weak scattering limit, basically you can get rid of this quadratic correction, and then your VK equation will reduce to the VFKL equation. Now, one of the silent features of the VFKL equation is that when you go towards larger and larger rapidity, this dipole scattering term will exponentially shoot. So, which kind of doesn't make sense because of the unitarity, and hence this non-linear terms are important in order to like tame the growth.
Isn't there is like a global minus sign because it decreased. This equation decreased. It describes the increase
In
as
the
a function of
scattering
yeah, but there's a
Yeah,
yeah.
so there should be a minus.
there is a minus. Okay. So the linear term as a plus and the other one as a minus. The quadratic term as a minus.
Minus, okay, yeah. If I remember right, that's how it should be.
This weak scattering limit is much less than 1 or
Yeah, when I have a diagram in.
No, I just want to know. That means the SX is very large, right?
Yeah, SX is large,
Large, and this is
and when you take
it's a weak scattering limit, or this is
No,
approximate
no,
one. Should be approximate 1, right?
no, the weak scattering limit should be smaller than 1. When
S is smaller than.
S is smaller than 1,
Not
yes.
1 minus S is smaller.
Oh, that's why I'm.
No, sorry. I define like my scattering limit. When I say scattering limit, so how do you define your scattering limit? Normally, this is how I define my scattering limit, and with 1 minus S4. And this is my weak scattering limit when the dipole separation is 0 and the value is 0.
Okay.
And this is when it hits the blackness limit.
So you actually expand S around 1, not
Yes.
dropping the S squared.
Yes.
Okay, yes.
Oh, okay.
S equals 1 is no scattering. S equals 1 is no scattering.
S equals 1 is it.
But that's where the product of two S's is as big as one S. So this doesn't jive with what the explanation that you gave us.
This too will
So
be,
what is the condition that you can ignore the first term with two S's, the non-linear?
when my scattering is, this term is small. No, sorry,
Oh.
no, wait a second.
Yeah.
When my 1 minus S will be small, so
Why can I then ignore S squared?
Why it's not right. Expand.
So you actually expand the first terms around 1. So I think it's not simply dropping the first term. Otherwise, the second interval.
It's after you have introduced the D. It's after you have it's a quadratic terms in D that you are going to drop.
Yeah.
yeah, maybe I can write everything in terms of the 1 minus S,
Yeah.
and that will help. So, and I call my 1 minus S has to be less than 1.
Yeah.
So overall, this is the condition that I want. I'm defining my dipole amplitude as 1 minus the scattering.
I understand that, but then you cannot drop the S times S versus the S.
You can drop the quadratic term coming from there.
You can drop the quadratic coming from D, but not from S.
From the D.
Yes.
But then I think the S squared term was effectively is the S.
No.
I think yes. What you want is you write to write S equals 1 minus D in the 3 terms,
Yeah.
and you want to drop the terms that are quadratic in D,
Yeah, so
not in S.
yeah, this is what I meant, like instead of saying
Quadratic
1,
D.
I should write everything as 1 minus D and then say there will be a condition when you can drop the quadratic terms. Yeah.
In D,
In D.
not in S.
Yes. Yes, in D.
Very good.
Yeah, re-summarizing, like write everything in terms of D and then drop the quadratic terms in D. And then this will give you the BFK equation. Okay, so far what we were doing is we were considering the quantum distribution in your dipole. So dipole had this gluon splitting, but you can also include this you can also include the information in the weight function, that is your shock weight. So what we say is that your weight function, that is the information contained in the nucleus, more and more gluons will be emitted, and hence you have to modify the weight function. And since you started okay, I can explain this to the picture. You originally had you were probing the observable at point x0 meters, and you had your small x particles and the large x particles. Now, when you're taking the observable when you're defining the observable at this new cutoff, you will have this window where new fluctuations are emerging, and these new fluctuations can act as your new sources. So you basically have to modify your weight functional so that you can take into account these new sources, and these new sources can generate your new gluons. So this is what the Jim-Wolf equation tells you, that instead of considering all the information in the dipole, you can consider the same information in your target, and that will help in understanding the quantum evolution. Now, one can refer to this paper where they say that how can one go from this focal plant form of the Jim-Wolf evolution to this Langevin form, which is kind of helpful in doing the pneumatics. And this is quite simple to understand because it basically tells you that Langevin form of the Jim-Wolf equation provides you the Wilson line at new rapidities. So it depends upon two terms: the Jim-Wolf kernel, which is integrated over the transfer space, and the alpha S, which controls the speed of the evolution. Now, Xi is your Gaussian noise, Vz is your initial Wilson lines, and Y is your original rapidity. And now, one of the problems with the Jim-Wolf kernel is that it has this Coulombic tiers, and you have to cut down the Coulombic tiers, and you do this by modifying the Jim-Wolf kernels to include this infrared regulators.
Can you go back?
Mhm.
Just want to understand that. The one more. So the separation between the source and the small parton in between the fluctuation.
Yes. So
how the fluctuation in this case is done.
So okay, when basically what I'm saying is you have your momentum, and you are just defining a cutoff based on how much momentum the parton is carrying. If it is carrying the larger momentum than this cutoff, it is called as the large x parton, and if it carries smaller momentum, then it is called the small x parton. So when you have something like this, then you can use classical dynamics. But now, if I'm moving this point to a new point, let's say to this point x0 prime p plus, then you have your large x partons again, and you have new small x partons. So you can again do the classical simulation by considering a new cutoff. But if you want to do it on the same place where you had the original weight functional, you need to go to this point, and this are your new sources. These new sources are taken into account by modifying the weight functional, and this modifying the weight functional information is contained in this Jim-Wolf equation. Yeah. So you have some semi-induced sources which can give rise to your new gluons, and that's how you take into account.
And that evolution, okay, so then on slide 17, that evolution become this Langevin
equation, yeah. I mean, you can write in terms of the evolution on the pneumatics, you can just update your Wilson line at each and new rapidities. Yeah. Okay, this was the plot I was talking about.
Yeah.
Yeah, so this is the effect of the Jim-Wolf evolution on the dipole amplitude. And so let's consider so the plot contains the dipole amplitude as a function of your dipole separation. Let's consider one of these curves. So what you see is that when the dipole dipole separation is small, the dipole amplitude is zero, basically zero. That means that you cannot, they are at the same point, so 1 minus b times v dagger would be zero. And if you go to a larger dipole, you basically hit the black disk limit, and this is where the strong scattering. This is the strong scattering area, and this is the weak scattering area. Now, when you do the small x evolution, that basically means you are increasing adding more and more gluons, and this will increase your QS. So for a given QS, so for a given artwork, when you're increasing the QS, that basically means you are going into the strong scattering region more quickly.
You meant add more gluons to the source.
To the source.
To the source. Okay.
Yeah.
That goes up.
That will help you in getting the strong scattering region more quickly.
So doesn't this QS already act as an infrared cutoff? Do we need an extra regulator?
But we need extra. So normally when you have, okay, there are various places where the infrared regulator shows up. For example, one of the simplest one is when you have this classical Young-Mills equation, the Young-Mills equation. The Young-Mills equation reduces to your Poisson equation. So your if I have so when you solve your Young-Mills equation for a given source, it reduces to this thing where this is your I can write it in terms of the K model. So you will have like this K per square. This is basically like a long Coulombic tail. Now you need something like an infrared regulator in order to curb this behavior of ever growing gluonic field. Like you don't want you have your color source over here and your gluonic fields are like flying apart away from the nucleus axis. So this is where you add infrared regulator. Even though you have the saturation scale, you have to add these things by hand to curb this behavior. And similarly with this gym work evaluation, this K's are basically your x minus c over x minus c squared. Again, you have something which is like Coulombic tails, and you need to add infrared regulator by hand to.
Yes, your infrared regulator that you are introducing in this picture, it still doesn't do confinement. You still do something to take.
So these are something that it helps you in confining this.
Yes, exactly. Yeah, you still need an extra one
to confine
to confine
the knowledge.
Which is not productive.
But this is the reason whenever we say that there's huge uncertainties involved, even if you have like a large x and between this large x and the small x. Degrees of freedom.
Are these two scales are self-consistent in the sense that if you choose different values
of QS?
Well, so, if you change the M, do you need to change QS? I mean, are they?
Okay, no, but the thing is like how we normally do simulation is like QS is something that we have, but the infrared regulator we fix by matching with the data.
Okay.
Yeah.
So isn't it always like something like the pion mass?
No, not always, not always. Like you can start with the random values, and when you want to fix the fit with the data, you see that okay, maybe your pion mass is not helping you. Okay. Yeah. Let's revisit the color glass condensate case in order to add one more point. So far we saw that all the neutron structure at small x can be characterized by this correlation functions of the Wilson line, like we saw the dipole correlator, which were expressed in terms of the product of the Wilson lines. Now you have this another theory developed by these people, where they say that you can use this high energy vectorization in order to write down your single inclusive observables. So when I say single inclusive observable, for example, multiplicity at a given rapidity can be expressed as a convolution of the functionals of the Wilson lines. Now, instead of writing like this, I used this expression from this paper where they say that in order to calculate the multiplicity, you have this weight functional for the projectile and the weight functional for the target, and they are at the rapidities where you want to calculate the observable. This will be more clear from the next slide. And this rapidity, just because your weight functionals are modified at each rapidities, you take this into account by using the Jim-Walk evaluation equations. So in simpler words, for example, like I'm using this 3+1D alpha model. which takes into account your classical Young's equation, and the modification of the weight functions are taken into account by using this QCD Jumbo evolution. Now the picture says that if you want to, if you have, like, let's say this is your projectile, this is your target, again, same projectile and target. Now, if you want to calculate an observable at mid rapidity, for example, over here, the evolution, the projectile and the target will be evolved by the same amount. But if you have to calculate something in the forward or the backward rapidity, for example, somewhere over here, then this, like, this will be evolved less compared to this thing. So this is how you consider collision. So let me talk about the 3+1 DIP plasma model nowadays.
So the Jimbo evolution, what is the starting value when you do the evolution?
So you consider, like, for example, you like, let's say you are doing okay, from, you always fix a value, like, let's say
X of
x, yeah, we always
Oh.
fix the value of the x, and that is the point where your original Wilson lines are defined, and this will act as a starting point.
typically is energy dependent, right?
Yes.
What was the value?
I'm like let's say 10 power minus 1 or 10 power minus 2, and then you, the x value is 1, and then you go further down from there. Yeah, let me define the 3+1 DIP plasma model. So you start with by generating the configurations of the Wilson lines at some initial rapidity. And once you have this initial rapidity, like for example, in the 3+IP plasma model, people use this IPSat instead of this MB model. So this IPSat model provides you this QS, which is a saturation scale in terms of this impact parameter and the momentum fraction after fitting to the head adapter. Now, once you have this Wilson lines at an initial rapidity, you evolve it to all the rapidities of interest using the Jimbo evolution equation. And once you have the rapidities, Wilson lines at all the rapidities, you just collide them like 2+1 D, like 2+1 DIP plasma to construct the full 3+1 D results. This is just to emphasize on the fact that for the results that we'll be showing today, everything has been done at mid rapidity. That means both the projectile and the target has been evolved by the same amount. Now,
Sorry,
Yeah.
I'm confused. You call why in it the rapidity separation? That's the rapidity separation between product and target, projectile and target?
this thing is where you want to compute the
Yeah, I
observability.
know.
Yeah.
What is y init?
By init is the initial point where you have the rapidities defined, Wilson lines defined. So-
Okay, so it's not the separation of rapidity
No,
between
no,
projectile and
no, no,
target.
no, no.
Okay. So what does separation mean? Separation from what?
So separation means the point where you want to compute the observable and where your projectile's initial rapidity was.
Okay.
I'm so sorry for this lack
No,
of
it's very
preparation.
good. As well, you can ask this detailed question.
Okay, now let me talk about like how this 3+1 DIP plasma model people define their color charge densities. So first of all, you sample the position of the nucleons using some distribution. Over here, most of the time I'll be using the Wood-Saxon distribution. And once you have this nucleon position, you use the IPSat model to fit the header data to get the values of your QS squared. And this QS squared is something that is related to your G squared, U squared, which is something that you saw in the MB model. Like if you want to define your color charge density, you need to have the information of the G squared, mu squared. Now, once you have the G squared, mu squared at each transverse space, at each point in the transverse plane, you can sum over all these quantities to get the G squared, mu squared of each nucleus. Over here is an example of like the G mu of the projectile as well as of the target, and the lumpiness, and you see that it's quite lumpy based upon where it is being defined. Now, once you have this G mu for both the nucleus, you can use the color, you can sample the color charge density from the 2-point function that was defined in the MB model. Now,
So this G squared, mu squared is the IP plasma analog of the nuclear thickness function in Trento, for example.
exactly. Now let's have a look at the effect of Jimbo evolution on a particular nucleus. So over here is an example of a lead nucleus taken from this paper, from this particular paper. And what you see is the transverse structure of the lead nuclei at 3 different values of the rapidities. This is your initial rapidity and initial rapidity. Now, when you go towards larger rapidities or towards a small x, you see that there is a kind of small growth in the small overall growth. But as you're going towards the small x, you are basically increasing the QS, and the relative scaling, the relative transfer scaling, that is 1 over QS decreases, and hence more and more finite structure emerges. So if you compare these two things, you have more finer scaling emerging from this thing. So this happens because more and more gluons are reduced, and this will kind of smoothen out your
What's the starting rapidity?
y is equal to minus 2.4.
Okay, that's where you start.
And then
How do you get that initial density?
So initial density is what you get it from you have your color charge densities, and then you use your Langmuir's equation to calculate the gluon densities. And
Oh,
this-
so
this
this
is
stuff
basic-
is like the source plus the
Gluon
gluon
density.
field.
Yeah, gluon field.
So I
And
was
this
wondering
is-
how the source look like.
So no, normally you just
Just a global model, the source.
no, this is just the gluon density.
Okay.
You have plotted it using the trace of the Wilson lines. So you had your color sources. You solve the Poisson equation. This is the equation I was talking about to generate your gluonic fields. And then you use 1 minus real of trace of the Wilson line to have this thing. And if you want to, okay, we never do we have a source somewhere? No, I think we never.
And I think because of the information, I think the question of Django was that the color, the structure of the LED, it enters at the level of the sampling of the no color sources. So how do you sample these,
Okay, so for one thing,
right?
you can imagine that there's a one-to-one mapping. You have your color sources, and where the color sources are sitting, you will have your gluon densities surrounding those color sources.
Those color sources effectively is like it's like Wood-Saxon.
Distribution, yeah,
nucleon.
yeah. You have your nucleon distribution, and this at the point of your nucleon distribution, you will have your this thing. So the overall geometric shape, which has been captured with your largest partons, will be shown by the smallest partons. Like if you just plot your nucleon position using the Wood-Saxon distribution, will have roughly the same shape as this one.
So each nucleon you describe as
Color.
three
Color.
quark sources. Okay, and
Yeah.
each quark source then has gluon
Gluon
cloud and
fields.
that.
Overall, this will be the geometric shape. Okay. Now, so this is one of the recent work by Heike, Farid, and Bjorn, where they look at the nuclear geometric profile by studying this exclusive vector measure reduction. And the idea is that, if you measure, like when you study this particle production, you can basically get the information about this transfer, momentum transfer. And since momentum transfer is the conjugate of your impact parameter, that will help you in studying this, doing this nuclear imaging. Now, what they do is they use this ultra-peripheral collision. That basically means that the strong interactions are suppressed, and one of the nucleus will act as a source of the photon, and this will probe the other nucleus. Now, what is shown over here is this nuclear density thickness as a function of the impact parameter, and this nuclear density thickness is given in terms of the cross section, since it will be a diffractive cross section, it will contain this ups and downs, and this minimums are covered by this minus 1 raised to the power n. Now, when you plot it as a function of the impact parameter for 3 different values of the x momentum fraction, along with the Wood fraction, so Wood fraction is basically how the nucleons have been sampled. So this dotted blue curve is how the nucleons are sampled, and this is basically acting as a reference point of how the gluon density will affect this nuclear density thickness.
That's the n in the minus 1 to the n.
N is the number of the diffractive minima.
So the center and the tail evolves in opposite direction.
Yeah, let me explain this thing. So what you see is that each curve, this curve, has 2 distinct regions. First of all, the small impact parameter, and the other one is the large impact parameter. So at the small impact parameter, what will happen? You are basically in the center of the nucleus, and the gluon density will grow. So gluon density will grow, and on the ends, as already seen over here, the periphery, there is a small growth. There is a small growth. So at the end, the size of the nucleus will grow. Now, since you have to keep this thing, this overall normalization constant, the area under the curve will remain same. So when you go towards larger, smaller x, the overall plot will shift.
So the growth at the edge comes from a growth of the nuclear, which comes from a growth of the gluon
Cloud
clouds.
density, yeah, at the periphery and
But it's also partially the normalization, right?
yeah, this is the normalization that is basically shifting.
If you require the integral equal to 1, then it will always scale back if the center goes down, right? I mean, that
Yeah.
also play a role, but of course, there's additional fluctuation, broadens the tail, but two effects, they both contribute.
Right.
What causes the slight wiggles?
This thing is captured by using this integrating between two different values of the momentum transfer value.
Do you have the spectra that the gamma for
Okay,
that?
first of all, this work is not done by me.
Yeah, but I want to see.
Yeah, what I
But
mean,
it's okay, it's okay.
this-
Maybe afternoon, I would like to see how the structure in this UPC, the T spectra, give you this kind of wiggle.
okay, maybe I have to look at this paper.
Yeah, if you
I
get the
was
slide.
just interested in this particular plot because it kind of captures the information that you saw in the previous
Yeah.
slide.
But how many diffract peak is like, the first one peak is give you the main feature? Or you have
Okay, I
to,
have no clue about this thing. I
I
need to,
think the wiggles presumably come from J0,
this is the, yeah, the business mention, you put with the reason.
from the Bessel function.
Mention. Then maybe in the discussion now we can look at this.
yeah,
paper.
yeah.
I just remember they had this curve for the diffractive and not how many peaks and curves or something like that.
With some diffractive model. or something.
Yeah, you have like the cross
Which is
sections even in terms of.
that's
It
the-
looks like a G.
But is this but if I look at the N is like some independent variable here. What do you mean by integrating? You're integrating the delta. What is delta?
Okay,
Delta
that
is
is
the-
the momentum transfer from the nucleon to your Gibbs side.
Right, which is the x-axis
Mhm.
of is a T or
This delta, delta is the momentum transfer. Okay, you have to look at this paper to see the
yeah,
more
I will
details.
write down. We'll discuss it.
Yeah, read this discussion. I was not involved in this work at all, so I have no clue what these people are doing. Okay, now let's have a look at the effect of Zimbabwe position on some deformed nuclei. So over here I'm using like a fictitious nuclei, like uranium, but it has a large deformation value. So, so again, we have the transverse profile for 3 different values of rapidities. Y is equal to -2.4 is my initial rapidity. And when you see that when you go towards larger rapidity, the shape of the deformed nucleus kind of remains intact. What you are seeing is basically more and more finite structures are emerging inside the nucleus.
Doesn't it grow both in the Y and in the X direction?
Yes, but
That should reduce the X, the beta 2 a little bit.
this will reduce it, yes, but the like the shape is modified like by, I would say hardly by 10%.
Okay.
Yeah. Yeah, this information is captured in the centricity. Now instead of now this is for the real uranium nucleus with the exact with beta 2 is equal to 0.28, which is the deformation parameter. And yeah, over here what you see is that the eccentricity as a function of your energy. And even if you are seeing this -2.5, that basically means that energy has been scaled in such a way that you can set your compare it with your rapidity values. So you're going from low energy towards high energy, and you see that the epsilon 2 kind of remains the same, but epsilon 3 and epsilon 4, which are more which has something to do with the fluctuation, are the one that reduce a lot. And this is kind of more evident from this ratio thing, where epsilon 2 is hardly changed, but the epsilon 3 has changed by like 20%, and epsilon 4 has changed by like 10%. And yeah, okay, just to emphasize again, all this evolution has been done at the mid rapidities. You
But
are seeing the results.
But this epsilon, the starting point, the eccentricity, epsilon 2 contains a huge contribution from the beta 2.
Yeah,
And while the others are all fluctuation, right? I mean, the initial epsilon 3 is already just purely fluctuation.
Fluctuations, yes.
But what I mean is somehow when you have a global shape, then fluctuation doesn't really change it. Right?
So you, okay,
I-
you
I-
basically.
I don't know what happens if you do this for spherical.
Three, for
For if you set the beta to equal to 0, how this will happen?
So if you have a spherical, so okay, it's over here, what is happening is like you have some fluctuations coming from the nucleon side, like the position of the nucleons, and some fluctuation coming from the deformation. They both are playing a role in setting up the people. But if I understood your point. If you had like just a spherical nucleus, you would assume that when you average over all the profile, average over all these fluctuations, this will give you 0. epsilon 3 would be 0.
No, but I'm saying the behavior of epsilon 2 for a spherical system, they look similar to epsilon 3.
So first of all,
Because epsilon is all fluctuation. Now let's assume epsilon 2 is also all fluctuation. This is the p equal to 0, so it's all fluctuation.
yes.
Would that decrease by the same amount as epsilon 3? Because right now it's hard to tell because there are two effects competing.
Yes, okay, this is something that maybe we can check, but
I'm not sure what you are calculating here. Is this a zero impact parameter full overlap or what?
so these are the deformed nucleus. These are at randomly oriented nucleus.
All oriented.
Random, right? And all impact parameters. So
At B equal to 0.
Equals 0.
is it p equals 0 but all orientations?
All orientation is into account, yeah. So maybe for spherical nucleus, I'm like,
But the epsilon 4 decrease also weaker because it have a nonlinear contribution. The epsilon 4 actually receive a contribution which is like a beta, epsilon squared, which also sees the global. This-
geometric shape.
yeah, so that's why epsilon 4 also decrease slower.
Okay, now let's
So,
do it.
I'm sorry, I'm trying to think through this. So these epsilon n's tell you the effective eccentricities that you see at mid rapidity if the source is 4.8 units of rapidity away.
Yeah. Or maybe you can, if you don't want to think in terms of the rapidity, it would be much easier to think in terms of the energy. Like if you go to a high energy, they both have dependent quantities, energy and rapidity are dependent quantities. I just wanted to see like if you take the values from the low energy people and compare the high energy, like will the eccentricity remain the same or it will be changed by some factors? Okay, now let's have a look at the effect of the Jimbo accumulation on the small system. So for a small system, this is one of the crazy nuclei which has like a huge dramatic effect due to its clustered structure. Again, we see that when you see it at a larger rapidity, like y equal to 4.6, the overall shape kind of remains the same, but you have more structure emerging at the center of the nucleus. Like there's a growth in the number of the black holes. Now over here I have compared two different distributions. So this is the Wood-Saxon distribution, and this is the information coming from the PGCM. So first of all, we see that Wood-Saxon kind of captures the overall shape, but the two distribution have the PGCM looks much more closer to the actual shape of the neon nucleus that we're used to, like a billiard pinball shape.
Did you explain it at the beginning? Sorry, before I could come, what the PGCM calculation is that you're using here?
Can somebody from low energy please tell me what is PGCM? Like I just know I got the position of the neutrons and
So you got samples.
yeah.
I guess Giuliano who gave you that.
Yes.
So this is my calculation. I was not aware.
But your calculation just provide beta 3 and all those beta values, right?
So that means like the PGCM for neon 20.
Yeah.
This one is it comes from a PGCM calculation with German Newtonian. And so here I computed the density at the average deformation beta 2, beta 3, and beta 2, 2. And
putting into a global model.
So I gave to Giuliano the full density.
Then he
The
ran-
the
probably,
non-body
yeah,
density of the mean field state. And then I don't know what to do.
And then Giuliano sampled that, or did you sample it, or what?
No, I sampled it. He just gave me the position of the nucleons and I
No,
sampled
so
it.
he sampled it.
Giuliano pre-processed.
So he sampled this numeric density somehow.
Yes,
Some
I think
projection
in
sampling or
that
something.
case, I mean, it did that for some other thing where you use the real density and not the exact. No,
Please there, we can ask him to.
Yeah, I just got one file which has the position of the nucleons and that's
Okay,
it.
okay, fine.
Nope,
Keep going.
we can't defend himself.
Okay, so this was one of the questions that Giuliano was basically interested in, that if you do the Chibok evolution on small nuclei, whether will the shape of the nuclei be melted because of the Chibok evolution? And the answer is no. The small X evolution does not melt the bowling pin shape. Okay. I'll say it in advance. This is a disclaimer. This is like one of the preliminary results, and we are having a hard time understanding it. Like, from here on. So, okay, this is like the eccentricity for the neon 20, again at p equal to 0, that is central collision. And I have I have looked at the eccentricity epsilon 2 and epsilon 3 for three different types of, like, two different types of distribution, but along with the fixed PGCM. When I say fixed PGCM, that basically means this one particular orientation has been taken into account, and the random PGCM takes the average over all the different kinds of orientation. And then
So
we
what
say
is that fixed orientation?
this is the
Full overlap of both.
Yeah.
this shape
So, yeah, okay, so both of them have the same shape and they are
yes.
completely aligned
aligned with the
and perpendicular to the B direction.
But exactly, right. So as already expected, the fixed PGCM has this overall elliptic shape. So the epsilon 2 of the fixed PGCM is larger, and it decreases when you go towards large energy. Random PGCM and random root section are in the same ballpark, but the decrease is kind of faster compared to the fixed PGCM. And we are suspecting this could be like it would be hard to destroy the overall elliptic shape, but the eccentricity arising due to the fluctuation would be easy to kill. This is what we expect, and that could explain like why in fixed PGCM there's a smaller decrease in the ellipticity, but in the random PGCM and the random root section, the ellipticity.
These epsilon 2 are calculated as a root mean square, right?
Yeah, these are the
So that means there's a very large contribution of epsilon 2, probably dominated by the spherical,
yeah.
right? So that one is easy to kill, but the stuff you superimpose on top is.
It's hard to destroy.
Right.
Yeah.
So when you have a random PGCM, look like that component is small.
The overall ellipticity.
Yeah. So
Yeah.
I'm saying that the difference between the two states, that because this is coming from the average geometry. I'm saying the decrease most likely is the dilution of the random component.
This is true, but I just wanted to know why in the random PGCM the decrease is more compared to the fixed PGCM.
Because
Like
in the random PGCM, the average geometry component is very small.
Small.
Like you see, it's only between the blue and the green, that component is tiny, but that component stays the same. Okay.
Not tiny, it's 60%. It's a suppressed zero.
Are we talking about the same thing?
No. If you look at the zero, right, your starting point.
Yeah, but the zero of eccentricity is well below the board.
Yeah. So that's why
So we are suppressing the fixed orientation eccentricity by 35% to.
is this random W section also content deformation or not?
Yeah, everything that is deformation.
Okay.
I think you got my question. Like if I take the ratio of this and this point, this will be small compared to this.
Yes.
Not the ratio, you have to take the quadrature difference.
Why?
No, the ratios.
Ratio is fine. Like I just want to see what are the effects of the evolution.
But he's saying that the difference of the quadratic is epsilon 2 squared on one side minus epsilon 2 squared on the other side. It might be the same.
I think they were the same.
But
Yeah.
is it like from the picture?
No,
it
I
doesn't
think
seem
I think we should write down this.
Question. Try the question.
It's a question.
But I have also a question that
all of them are Wood-Saxon, right? Because so you are fitting the Wood-Saxon potential with the VCM.
No, actually, it's
I don't think we
mean,
know.
if I understood what Julio did, I mean, from some of the calculations, right now, if it's the same thing, method he used here, he use a real density of samples and
But he sampled
So we
directly that numerically, or did he fit it to Wood-Saxon and
No,
then sample
no,
Wood-Saxon?
no, precisely. There was no Wood-Saxon, at least in one of the four some other. But I don't know if
Otherwise,
it's the same.
it would look like it.
Exactly same.
But the difference is small.
It would look like what?
No,
So
the PCCM and random WS are very similar. Right?
Yeah, they are in the same ballpark,
Yeah,
that's
it's,
one good thing.
it's almost the same, yeah.
Yeah, so we can continue using
But
this.
can you do the fixed Wood-Saxon?
I can do it sometime, but I don't have the plots for the fixed root section. Okay, so first one,
Can you go to epsilon 3? Epsilon 3 is the same.
yeah, first epsilon 3, it seems like all of them decrease by the same amount, and this might be due to the nucleonic fluctuations, that the same amount of nucleonic fluctuations are there. Yeah.
How many slides do you have?
How many?
Oh, sorry,
Just curious, because we have two talks in the second
We can
session.
give you you
We're
can
a little more
continue
important to stay on
afterwards.
time.
no, let me finish. Just it will hardly take like, I don't know.
No, but my question is, the question will be,
Shall I stop over here then?
Take a break and continue.
no, we have afternoon, yesterday, we have another 1 hour talk from the morning. That's okay, right? If we continue from 2 and then you can give a 1 hour talk, unless you are busy with something else.
Oh, I'm not busy, but
How much can you cover in the next 10 minutes?
I think I
No,
will,
but-
I'll just run.
But then we can ask questions.
We can keep the questions and then
We still have
just.
two other talks.
Yeah.
That's the
No, it's
problem. So
okay.
we have two talks in the second session, so we do have to stay on time. We don't want to push
Yeah.
this.
No, we
far.
won't, we will have, I think you will not want to lose time, you have more time.
Okay, and yeah, I think you guys will help me understanding the results.
Yeah. Thank you very much.
Yeah, any last minute questions?
That was a short talk.
But just to have this question on page 24, I'm sure you have it. So we always have this problem of Bayesian analysis that when we fit the Newton web, it's always prefer very large values. So do you think this is maybe also be the reason that in A collisions, the actual profile you need to determine centrality are actually wider than the suction include?
No, but this has something to do with the gluonic fluctuation, that when you are evolving it, the last density of the gluons is helping you get the, how do you say, increased
So
profile.
for example, I define my most preferred collisions as just producing one pair of hadrons.
Mhm.
So, but that little tail will produce sometimes one pair of hadrons. That will change, right?
You
Oh,
are,
no,
I
it's
think
fine.
you are onto something really important here. Because what we are assuming is that when we adjust our Wood-Saxon parameters to the cold nucleus in the rest frame, that we can use that distribution as the nuclear thickness function for stuff that's getting produced at mid rapidity. What she tells us is that the gluon distribution that is probed at mid rapidity is wider than the distribution of sources in the projectile. And it's wider by, well, this amount that you can see there, right?
Below
Because when we do the Bayesian analysis, it gives us a Newton west of almost close to 1 Fermi. But if you use that 1 Fermi to determine number of participants for hard processes, it's completely not favored by, for example, high PT scale.
So when you say this 1 Fermi, is it constant for all the kind of nucleons?
I'm not sure whether it depends on beam energies, and we do check that and gold. But I think we always assume the same Newton web across all different systems. It's hard coded in that way. We have not Newton web. At some point, and it prefers a very large